Welcome to Lecture 59, in which we're going to go to the diametrical opposite of the previous lecture. In the previous lecture, number 58, we were looking at elementary particles, the quarks and the leptons, that make up matter and make up the entire universe. In this lecture, we're going to go and expand our horizons to cover, in both space and time, the entire universe. And the way I'm going to do this is to begin with a history, which I'm going to call a history squared, because it's not the history of the universe. We'll get to the history of the universe at the end of the lecture. But we're going to start with a history of the universe. So the history squared of the universe. And I'm going to give you the story of evolving human understandings of what the history itself of the universe has been. The remarkable story here, the real takeaway message, is that the universe does have a history. It didn't have to have had a history. It could have been basically a static place that was always the same. But our modern understanding is very different. It's of a universe that began in a very different state than it is today, and that has been evolving ever since and is evolving today. And as we'll see, in very recent years, we learned about some surprises the universe has been throwing at us in terms of its history and evolution. So let's begin by looking at a history squared of the universe, a history of our understanding of the history of the universe. Around 1900, there was a widespread view that the universe had always been essentially as it is today, or as it was then, which is pretty much as it is today. The universe was a static place. It didn't overall evolve. Now, individual stars evolved, planets evolved, life evolved on Earth, history happened to human society, things like that happened. But overall, the big picture, the universe was basically a static place. And in those days, that meant it was populated with stars. And that was basically all we knew there was. In fact, that belief was so embedded in the popular culture and also in the scientific culture that Einstein, in 1917, added a so-called cosmological constant to his theory of general relativity. And the reason he did that was one of the first things that came out of general relativity was the idea that the universe must be either expanding or contracting. But it was believed to be static. And so Einstein added kind of a fudge factor. Now, he isn't quite fudging if there were other arguments for putting this term in. But by putting this term in and adjusting its value, Einstein was able to keep his universe, as predicted by general relativity, static. But then, just a few years after Einstein added his fudge factor to keep the universe static, Edwin Hubble began observations with the new 100-inch telescope on Mount Wilson in California. And he discovered one of the crucial ideas. There are really three crucial ideas here in exploring the history of the universe, and the first of them is cosmic expansion. In the 1920s, Hubble discovered the cosmic expansion. How did he do that? Well, we'll get to that in just a moment, but he was using this Mount Wilson telescope, and he looked at what distant galaxies were doing. He also was one of the first to really study distant galaxies. In the 1930s and 1940s, as a result of this cosmic expansion idea, there emerged the Big Bang scenario, the idea that the universe began in some kind of cosmic explosion billions of years ago and has been evolving ever since as the outcome of that explosion. There were competing theories. In 1948, Bondi, Gold, and Fred Hoyle put forward a so-called steady-state universe. They managed to preserve a universe that didn't evolve, didn't change in time, with a theory that nevertheless was consistent with cosmic expansion, and the result of the consistency was that you needed to create new matter out of nothing in order to populate the universe to the same density as it continued to expand. And these Englishmen happened to put it this way. They said it required one hydrogen atom to pop into existence in a space the size of Westminster Abbey every 3,000 years. So you weren't going to notice this going on, but the steady-state universe required the creation of matter out of nothing. And these three, who were leading figures in astronomy and cosmology, clung to the idea that the universe was steady state. In fact, it was Fred Hoyle who in 1950 coined the term Big Bang. And for him, it was a derogatory term, a dismissive term, dismissing the theories of cosmic evolution. But then along in 1965 came an observation that really swept away the possibility of a steady-state universe, made it very difficult to reconcile that with observations. And that was the discovery in 1965 by Arno Penzias and Robert Wilson of the cosmic microwave background radiation, about which I'll have a lot more to say in this lecture. Around the 1970s, which was the heyday of particle physics, you'll remember from Lecture 58, in the mid to early part of the later half of the 20th century, there were particles galore all over the place, and around 1970 we began to understand how all that particle stuff fit together and how there really were a few more simple particles, and we understood their interactions. And particle physics began to inform cosmology, the study of the universe at large. So we began to have an interaction between particle physics and cosmology, and I'll say more about that shortly. In 1980, an important idea arose from Alan Guth at MIT. He posed the idea of cosmic inflation, which solved some problems which we'll see arose with the Big Bang theory, the theory of cosmic evolution. The big surprise the universe threw at us came in 1998 when we discovered that the expansion of the universe, which was expected to be slowing down as the expanding universe did work against the gravitational attraction of all the matter in the universe, so it should be decelerating, and experiments or observations were made to measure that deceleration. Lo and behold, it was found to be accelerating. And finally, at about the year 2000 and beyond, we entered what I call the era of precision cosmology. Cosmology, the study of the whole universe, had been kind of if you get it right within a factor of 2, you're good enough. And all of a sudden, particularly with satellite measurements, particularly of the cosmic microwave background, we entered an era of precision cosmology where we could measure quantities that refer to the entire universe with the kind of precision we measure many other things in physics, to several decimal points. And we'll see now how this history squared of the universe evolves by looking at these individual discoveries. So let's begin with the expanding universe. What Hubble noticed was that light from distant galaxies is redshifted. Now, before I just throw that statement out blithely, let me point out that about Hubble's time, before the development of the 100-inch telescope, it wasn't known for sure that there were distant galaxies. There were faint smears in the background in views with the biggest telescopes, and there was a debate about whether these faint smears were some kind of dust or glowing gas or something nebulae within our own system of stars, the Milky Way, or whether they were, as some people said, island universes, entire galaxies of billions of stars remotely far away from us, unimaginably distant. And as soon as the 100-inch telescope took its looks, we saw that these were, in fact, island universes and galaxies had been discovered. And Hubble began looking at the light from distant galaxies and studying the spectra of that light, and he found the light was redshifted. Now remember what the Doppler shift is all about from Lecture 18. In the Doppler shift, when a source of waves is moving away from you, its light is stretched out to longer wavelengths. Light, sound, whatever. Waves are stretched out to longer wavelengths. If the source is coming toward you, the waves are compressed to shorter wavelengths relative to you, and you see them blue shifted if it's visible light. If the source is going away from you, you see it red shifted. And so the implication is the galaxies are receding from us, and furthermore, with Hubble's measurements, he discovered that the galaxies are receding with speeds that depend on how far away they are. The farther away a galaxy is, the more rapidly it's receding from us. And the very simple mathematical relation that describes that is V equals h sub 0 d, where h sub 0, h naught, is called the Hubble constant. And it's the basic parameter that describes the expansion of the universe. By the way, you might think that puts us in the center of the universe. It doesn't. And I don't have time to go into great detail on this, but if the universe is infinite, every galaxy would see the same thing. It would see all the other galaxies moving away from us. And if the universe is finite, then it has a funny closed structure in four-dimensional space-time, and it would still be the case that every observer would see the same thing. So this does not put us at the center of the universe. It does not make us special in any way. But it does imply that for any observer anywhere in the universe, the distant galaxies are all moving away with speeds that increase with their distance and increase basically linearly with their distance. The implication, the universe is expanding. And we're not at the center. Here's a picture of the original Hubble at the 100-inch telescope. Here's the modern-day Hubble, is named for Hubble, of course, the telescope that in the last couple of decades has brought us wonderful new views of the cosmos and is about to be superseded by the James Webb Space Telescope. Here is a diagram showing you some photos, original photos from Hubble's work of some of the distant galaxies he's observed. You see a spectrum, and you see some spectral lines, and as those photos change to more and more distant galaxies, and on the right there's a graph which shows data on distance and recession speed as measured by redshift for these galaxies Hubble studied. So that's what's going on there on the right. So that's the first piece of evidence that we live in a universe that's evolving. The universe is expanding. And the only way it could not also be evolving, changing, is if somehow new matter were being created to keep its density constant. But we'll see very soon that that becomes basically impossible. Before we go on, though, let's actually do a calculation based on this Hubble constant, because it's an important quantity and it allows us already to get some important ideas about how old the universe is. So let's go over to our big screen. Let me ask a simple question here. The Hubble constant happens to have the value of about 22 kilometers per second per million light years. So if a galaxy were a million light years away, well, it really has to be quite a bit further before local motions get averaged out. But if it were, it would be moving at 22 kilometers per second. If it were a million light years away, if it were 2 million light years away, it would be moving at 44 kilometers per second, and so on. And so I'm asking us to estimate the time since the Big Bang occurred. Let's just make some simple assumptions, which may or may not be correct. Let's assume that the galaxies have been moving with constant velocities. That turns out to be not a bad approximation in a universe in which matter is pretty undense, in which there isn't a whole lot of matter. That assumption gets modified for the real universe, but not a whole lot, not by orders of magnitude. Now, a galaxy moving with constant speed v is today a distance d equals vt from us. Distance equals speed times time. And so what we're going to do here is calculate the time when that distant galaxy was near us. And our calculation is really going to work for any galaxy. And so we're going to find the time when all the galaxies were basically in the same place. And we're going to call that time the start of the Big Bang, the beginning of the universe, the time, the age of the universe. Now, Hubble's relation tells us that the velocity is proportional to the distance with this proportionality, the Hubble constant, h0, 22 kilometers per second per million years. So let's put distance equals velocity times time in this relationship, and we get distance is Hubble constant times distance times time. Distance cancels. So we're doing a calculation that really applies here to any galaxy, and therefore t, the time, the age of the universe, becomes simply 1 over the Hubble constant. So the Hubble constant is really important. Its inverse is approximately the age of the universe. Now, there are variations depending on what model you use, but it gives us a rough sense of that value. So that's 1 over 22 kilometers per second per million light years. Now, that is not a fun unit to work with, and it's going to be a little bit difficult to get that to come out as a time. We have to do some conversions. We've got to, and you could do it several ways. You could convert light years to kilometers, which I'm going to do, or you could convert kilometers per second to light years per year. Both of them would involve a little bit of math. I'm going to convert light years to kilometers, and then I'm going to do the numbers. So a light year is the speed of light, 3 times 10 to the 5 kilometers per second, 300,000 kilometers a second, times 365 days in a year, times 86,400 seconds in a day. That's 9.5 times 10 to the 12 kilometers. So now I can get the time. The time is 1 over the Hubble constant in that unit. So the Hubble constant is 22 kilometers per second per million light years times this conversion factor. That gives me 4.3 times 10 to the 17 seconds. Work out the number. And if you divide that by the number of seconds in a year, 365 days in a year times 86,400 seconds in a day, you get 13.6 gigayears, 13.6 billion years. So there's a quick estimate for the age of the universe. And in fact, that estimate we've done here is remarkably close to what cosmologists believe to be the age of the universe, the time since the Big Bang. So there's a quick calculation based on one of the early measurements, although this is now a modern value of the Hubble constant because our measurement of that value has been getting more and more precise over time. So we've calculated the age of the universe. Let's move on and look at other pieces of evidence for the evolving universe. Let's look at the cosmic microwave background. Here's a picture of Arno Penzias and Robert Wilson in front of a telescope at what was then Bell Laboratories in New Jersey. And in 1965, they were studying sources of noise in this telescope. It's a radio telescope, and they couldn't get rid of the noise, and they shoveled out pigeon dung from pigeons that were nesting it in case that was radiating some microwave energy, and they did all kinds of things. They pointed the telescope up at the sky, down at the ground. This energy was coming from everywhere. So the discovery in 1965 of this bath of microwave radiation permeating the universe and coming from all directions from these Bell Labs observations. Now, Penzias and Wilson knew there were cosmologists at Princeton University who had theories of the evolution of the universe that suggested at the time hydrogen atoms first formed in the universe, as the electrons collapsed to join the nucleus and form hydrogen atoms, they would emit photons as they fell into the ground state of hydrogen that we talked about in worrying about atomic theory. And that radiation, the electromagnetic radiation, the photons emitted in that process, as soon as we had hydrogen atoms, which were electrically neutral, they didn't interact much with electromagnetic radiation, and so that radiation would then be free to travel throughout the universe. The universe basically became transparent at that point, which was estimated to be about 380,000 years after the Big Bang. So Penzias and Wilson teamed up with the Princeton theorists, and they realized the significance of their discovery was they had discovered the remnant, the fossil radiation left over from the time at the beginning of the not the beginning of the universe, but 380,000 years after the beginning of the universe, the time when atoms were forming. And measurements showed that microwave radiation, if you plotted the radiance, the energy per unit wavelength, versus wavelength, it fit perfectly a black body curve, like those curves I've showed you before when I talked about hot glowing objects. Now, this is not a very hot object. The entire universe is at a temperature of about 2.7 kelvins, 2.7 degrees Celsius above absolute zero. But nevertheless, that's not zero, and so it's glowing, and this glow is the remnant of that radiation that was emitted when the atoms were first formed. It was much higher in energy radiation then, but it's been redshifted down to these much longer wavelengths by the expansion of the universe. And so there is the cosmic microwave background, a really profound discovery, and a discovery that theories that don't include a Big Bang and an evolution of the universe have a very, very hard time explaining. So this agrees well with the Big Bang prediction at the time of hydrogen atom formation at 300,000 years after the Big Bang. So that's the second of the three major discoveries. Cosmic expansion is the first, microwave background is the second. The third is this interaction with particle physics. For example, we now know that there was a quark-gluon plasma before there were formation of individual particles like protons or nuclei. About 10 to the minus 6 seconds after the Big Bang, there was this quark-gluon plasma, and we've actually studied it in the relativistic heavy ion collider at Brookhaven National Laboratory within the last few years. So particle physics is informing cosmology, and cosmology is also informing particle physics. And if you think way back to Lecture 1, I talked about that interaction between the large scales in physics and the small scales in physics, and how it's a two-way interaction. Up to about 1 second was what was called the Hadron epoch. By that time, things had gotten cool enough for particles to come together, quarks to come together and form protons and neutrons and other hadrons, but they couldn't yet come together to form nuclei. And then there was a really crucial stage in the evolution of the universe from about 3 minutes to 20 minutes, in less time than this lecture is taking. A really important thing happened. For the first time, hadrons could come together, protons and neutrons, and form atomic nuclei. And they could only form by this fusion of nuclei, deuterium, helium, lithium, and beryllium. Those were the only elements formed in the Big Bang. All the rest of the elements that make us up and other things up were formed in stars by nuclear fusion. But the Big Bang formed these things, and the abundances of these elements are very sensitive tests of early universe theories. And here what I've got is a graph that talks about the density of matter on the horizontal axis relative to photons, and the abundance of these different elements, these four elements: deuterium, the heavy isotope of hydrogen that we talked about in the nuclear physics lectures, helium, lithium, and beryllium. And those abundances are extremely sensitive to the density of matter in the universe. And observations, this is with the Wilkinson Microwave Anisotropy Probe satellite, more about that soon, very, very accurately pin down conditions in the early universe. So particle physics helps to confirm our idea that the universe is undergoing expansion and it's following from a Big Bang, and what we know about particle physics and how the particles interact and merge is completely consistent with what we observe. Another idea that came up in 1980 is an idea that was needed to overcome some problems with the Big Bang theory, because the Big Bang theory posed some issues. And this is the idea of the inflationary universe posed by Alan Guth in 1980, because there are some quandaries for the Big Bang theory. One is the so-called horizon problem. If I look as far away as I can in one direction, I see objects that are so far away that light took from the beginning of the universe to travel to me. If I look in the other direction, I see objects that are equally far away, and those two objects in the farthest distance I can see in that direction and that direction are so far apart that they couldn't communicate by light in the time since the universe has existed. That's a problem. It's called the horizon problem. How Is it then that those parts of the universe and those parts of the universe even look the same? Why should they? There's no causal connection possible between them. So inflation theory solves that problem. It also solves the flatness problem. We believe the universe is overall geometrically flat. General relativity tells us it's curved locally near massive objects, but overall it appears to be flat. It has large-scale structure, galaxies and clusters of galaxies and clusters of galaxies. Where did that come from? And finally, we don't see any magnetic monopoles, and yet there are theories that suggest there should be magnetic monopoles, those magnetic analogs of electric charges. How does inflation take care of all that? Well, here's a graph of time in seconds, very nonlinear graph, and something I'm just going to call the size of the universe, but you can think of it as the distance between two characteristic particles in the universe. Each tick on the vertical axis is a factor of 10 to the 20 in the size of the universe. Early in the universe, starting about 10 to the minus 35 seconds and ending about 10 to the minus 32 second, unimaginably small times, the universe expands very rapidly. There it goes. And then it continues to expand at a much more sedate pace. So there's the evolutionary epoch. And inflation solves all these problems because the points that are now extremely distant were at one point very close together before inflation. The flatness problem takes any kind of bending in the universe and by this colossally fast expansion flattens it out. Large-scale structure is associated with quantum fluctuations. Remember those zero-point energies? Nothing can have zero energy. Quantum fluctuations in the early universe are amplified by inflation to make the seeds of large-scale structure. And finally, maybe there were magnetic monopoles formed, but they were formed before inflation, and inflation dilutes them to such a great extent that we simply don't detect them today. So that is the idea of cosmic inflation. Now, that idea is, I would say, 95% solidly established. There are still people who think maybe inflation isn't quite right and has its own problems, but it's pretty firmly established. Finally, in 1998, we discovered something new about the universe. We discovered acceleration, the cosmic acceleration. We shouldn't expect this because cosmic expansion is happening against gravity, so gradually things should be slowing down. The galaxies working against their mutual attraction should be slowing down, and the universe's expansion should be decelerating. Just like when I throw a ball up, it slows down. So cosmologists, astrophysicists were trying to measure that deceleration. Distant galaxies should be receding more rapidly than a straight-line Hubble relation because distant galaxies, when we see them, we're looking at them as they were in the past because it took light a long time to get to us from them, and they should be moving more rapidly than we expected. The observation in 1998 showed that distant supernovas, exploding stars that give out a fixed, constant amount of energy, and so we can use them as sort of standard candles, astronomers call them, to pinpoint how far away they are because they're all the same, basically. They all have the same brightness. They were dimmer than expected, and the conclusion is that the universe is undergoing an accelerated expansion that began probably about 5 billion years ago. And on this graph, you see the redshift, a measure of how rapidly galaxies are receding from us. And on the vertical axis, you see a measure of distance, basically. And you see three curves. The red curve at the top is for a universe that was always undergoing accelerated expansion. The green curve at the bottom is what you would have expected undergoing decelerated expansion, and the blue curve is a universe that first decelerates and then begins accelerating again, and the individual points you see there are the data points, and they clearly fit the acceleration curve. So we've got something really unusual going on here in the universe. We've got an acceleration that started about 5 billion years ago, and we'll be spending more time in the next lecture exploring just what the physics may be that makes that happen. But we're far from having figured this all out, and yet this is one of the biggest surprises that's come to us in cosmology. Well, let me wrap up by looking at a couple other aspects of modern cosmology. I want to look at what I call the era of precision cosmology, and that involves the cosmic microwave background radiation in particular. Two satellites, COBE, the Cosmic Background Explorer, and WMAP, the Wilkinson Microwave Anisotropy Probe, which ceased operations in 2010, have provided us with these precision measurements of the cosmic microwave background. They give us maps of the microwave background, and here is what a map looks like. It's a very dull map. The plane of the galaxy is the horizontal plane in this picture, and this is a map of the intensity of cosmic microwave radiation, and it's completely the same. It is uniform to 1 part in 100,000. How very boring. But if you subtract away the average value, which is the same in all directions, you find something that looks like this upper right curve, and you see this big blob of blue and the big blob of red, and they are measures of our galaxy's motion relative to other things in the universe. Our galaxy has its own what's called peculiar motion, a little bit of velocity added on top of the general Hubble expansion. That's nothing of great interest, although it tells us something about our galaxy. So we can subtract that away. When we subtract that away, we get this lower right picture, and it looks pretty spread out all over the place, except for that bright band across the middle. That's our own galaxy emitting microwave radiation, Milky Way. We subtract that away, and the Milky Way emission subtracted, and we get this picture. And this is one of the classic pictures of modern cosmology. This picture shows areas of blue and areas of yellow and maybe little bits of reddish, and they're telling you blue is cooler material, red and yellow are warmer material. So there is a very slight variation at the level of about 1 part in 100,000, and the amount of information contained in there is staggeringly large and precise. And let me just give you a quick feel for it. How do we analyze this? Well, what we do is we treat these fluctuations as if they were waves of different wavelengths and amplitude. Now, you can see there's a lot of small structure detail in there. You know, it's 360 degrees around, so that whole map is looking at the whole sky, and we're looking 360 degrees around. So you can imagine that there are fluctuations, a lot of them, on the size scale of about a degree. So what we do is we treat these fluctuations as if they were waves, and we analyze them for how much amplitude there is in waves as a function of wavelength. And we make a plot of that. And here is what will become one of the most famous plots in our understanding of the universe. This is a plot of wavelength going from longer at the left to smaller at the right, and amplitude, actually amplitude squared, because that's what matters. The 90-degree stuff at the left, where there isn't a whole lot of variation, although you can see some variation on scales of about 90 degrees in that picture, scales that occupy a good fraction of the width of that whole plot. That has to do with photons climbing out of gravitational structures. The middle peak, the big peak in the middle, which with about a 1-degree scale, is perhaps the most interesting, and it's the one that tells us many things, in particular that the universe is flat. It is probably a residue of acoustic waves that were set up in the early universe, perhaps by inflation. And the other peaks tell us other things about the universe, and we can milk this curve for enormous amounts of precision data about the universe. And I don't have time to go into all those details, but that curve, which comes out of the picture above, contains just a wealth of information about the universe, and it is precision cosmological information. So let's end up with the big picture here. The big picture of cosmic evolution is this. The universe expands, and as it does so, it cools. As it cools, more and more particles are able to stick together. In that first second, quarks are finally able to stick together if after 1 second, to form hadrons. The hadrons stick together to form nuclei in that first 20 to 30 minutes, roughly the time scale of this lecture. Nuclei and electrons are able to stick together only after 380,000 years. Before that, it's too hot. If they stick together, a collision occurs and they go flying off again. So as the universe cools, more complex things can form. Eventually, atoms form molecules. Molecules form life. And in a throwback to Lecture 1, life forms consciousness. And here's this wonderful cartoon by the great 20th century physicist John Archibald Wheeler, showing the universe having evolved life, and then life looking back at the universe with its consciousness and understanding what's going on. Wow, that's a big idea. That's cosmic evolution. And if you'd like to see what that looks like more visually, here's a picture that NASA has produced in connection with the WMAP Cosmic Microwave Background Satellite. In the vertical direction, we're looking at sort of size scale of the universe. Think of it as the distance between two particles, two galaxies, whatever. There is this beginning, the Big Bang itself, about which we know nothing because we can't push back that far because our physics isn't good enough. Then there is this inflationary period at about 10 to the minus 32 seconds. Very rapid expansion in the size of the universe. Then the expansion becomes more sedate. The cosmic microwave background forms about 380,000 years after the Big Bang event. The first stars form about 400 million years later, and then we have a long period of formation of stars and galaxies from about 400 million years on to the present. Acceleration began about 5 billion years ago, and here we are 13.7 billion years out from the Big Bang. Cosmic evolution. Let's wrap it all up with a quick summary. We've got cosmic expansion as one of the big ideas. Hubble discovers it in the 1920s, the microwave background in 1965, and particle physics ideas. These three things come together to give us the picture of the universe that we have today. Inflation 1980 solves some problems associated with the Big Bang theory. There's the inflationary picture. Acceleration in 1998 throws a new monkey wrench into the works, which we'll explore more in the final lecture. And precision cosmology from 2001 on roughly gives us these really careful, detailed measurements of a lot of aspects of the universe. And there's that classic picture now from the WMAP satellite of the cosmic microwave background. And so the overall picture, we expand, we cool, and we get structure, and ultimately we've got consciousness.